Welcome to this lecture where we're going to talk about Project 1, which is how to solve a maze iteratively using data structures. So we're going to go over this project at a high level and describe the important parts. There's a lot of detail here, so you really should read the project description even before you watch this video, and I think it'll make a lot more sense. We're going to talk about the overview of the project. We're going to talk about how the maze is represented and the data structures involved. We're going to talk about the central algorithm that we'll use, which is depth-first search, and we'll talk about how iterators are used in this project. The overall idea here is that we're going to solve a two-dimensional maze by reading in a textual description of the maze. And the textual description has a list of valid locations, also a start location, also an end location. Every location is a pair of row and columns, so such as 3, 4, okay? And then we're going to use depth-first search, or DFS, to find a path, if it exists, from the start location to the end location. And then if we found a solution, then we print that solution. So conceptually, our maze might look like what we see here on the left, where the start location is here, the end location is here, and we want to find a path from the start to the end using the valid locations, which are the start, the end, and every X that you see here, okay? So there are many paths that we could use, right? We could go this way, but that's not actually what we would do in this case. We could go this way, and that actually ends up being the path that we would find for various reasons that we'll go into later. But again, this is just a conceptual representation of the input. The input actually looks like this. It starts with a number, which is the number of valid locations that will appear after this. There are that many valid locations, 13 in this case, for all of these that you see here, 4, 6, 10, 13, okay? All of those valid locations, and then of those valid locations, 2 are special, and we list them at the end, the start location, then the end location. So we read the input in this format, but conceptually it looks like this. We're going to have a number of different data structures for representing all of this data. First of all, and importantly, we have a location class, which has a row, a column, as we've talked about, and in addition, a variable which we'll use for iteration called next direction, which indicates which direction the location is pointing for the next neighbor that we might want to visit. And it knows a location is a class or an object that knows how to iterate over its neighbors. So it implements an iterator pattern. The maze class is perhaps a little bit dumber than you might think. It only keeps track of what are the valid locations, what is the start location, and what is the end location. It basically just holds this information, and it can tell the user this is a valid location or it's not, and this here's the starting location, and this is or is not the end location. But the maze class does not contain any of the logic for actually solving the maze. There's a location stack class, and all it has is a top pointer because this is a linked list based stack. And it's used to store the path, which is an essential part of our search strategy as we move around the maze. So the stack starts at the starting location. As we move around the maze, we push onto that stack the positions where we visit. And that forms a path. So the stack is in essence a path, and it knows how to push and pop and also print itself. And there's also a class which we'll use as the node for each object on the stack, which is called a location stack node. Then there's also the driver, and the driver, of course, is not a data structure, but it does most of the work. It reads the input, or at least tells the maze to read the input. It solves the maze using depth-first search, and then it tells the stack to print itself, okay? Now, we're going to use for this project a strategy called depth-first search, or DFS. DFS is a very widely used method. It's a very common method for searching all kinds of things. And it's not just for mazes, though we are employing it here. And the term depth first, as opposed to another type of search strategy, which is breadth first, B-R-E-A-D-T-H, breadth first search. Here, depth first means we're going to always go as far as it can, or the driver is going to search as far as it can in the maze in some direction. That's left, right, up, or down. And as it visits more and more locations, as it hops from valid location to valid location, it's going to push these valid locations onto the stack. That becomes the path. If it ever gets stuck, then what it will do is it will back up, which means it's going to pop the stack because the stack is the path. And then after it backs up, it's going to go in a different direction than what it went last time. Okay. So depth first search uses this stack to maintain the path from the start to wherever the current location is. Wherever we currently are searching is the top of the stack. Keep that in mind. We could have used recursion to solve this problem instead of an explicit stack. If we did that way, then the function call stack would be replacing the explicit stack that we're using in this project. So we're not using recursion here, but instead we're explicitly keeping a stack of the nodes that we've visited. Depth first search is going to end in one of two ways. Either we have found the end location, which means that the end location is at the top of the stack, and the maze tells us that that is the end location, or when we have searched the entire maze that we can reach from the start, and we still haven't found the end, and therefore we've popped everything off the stack and the stack becomes empty, and that means that the maze is not solvable. Okay? Now, the order in which we explore in depth first search matters here, especially since we're trying to get an answer that matches your answer, if your project matches exactly what my project's implementation will do. So the driver is going to run depth first search with a location stack to keep track of the path, as we've said. And each time we have a location on the stack, that location represents a row and a column, but also it has that extra variable. If you go back up here, remember I said there's this next direction field that keeps track of what the iterator state for a location is. And that next direction can point in one of four cardinal directions, left, right, down, or up. So if we have, so every location knows where its next neighbor is, and it can move right. The order is actually right, down, left, and up. Okay. So if the current location is at the top of the stack, then what we would repeatedly do is the following. This is the basic search strategy. If the current location is done, then that means that the current location has no more neighbors. That's if we've gone right, down, left, up, the last state is done after up. And therefore, we're going to pop the stack. We've hit a wall. We've gotten into a dead end. We need to back up. And backing up means popping the stack. If we haven't hit a dead end, however, we're going to ask the current location, again, that's the top of the stack, for its current neighbor. Then we'll advance the current location's iterator. So if the current location was pointing to the left, then we would advance the current iterator's next direction to up. Okay. Then we would determine if the neighbor to the left in this case, is both valid and not already on the stack. And if it is both of those things, it's both valid according to the maze and it's not currently on our path, then we would push the neighbor onto the stack so it becomes our current location. So we've advanced one position. And notice that when we do that, what was our current location, moved from pointing left to pointing up. Therefore, if we ever have to backtrack to that position, the next time we try to go to its neighbor, it will go up instead of left again. Okay, so let's take a look. This is all a lot of complication. Let's take a look at the demonstration of the maze that I showed you earlier. And here's, I wrote a little program that demonstrates what is going on here, okay? Now, our current stack has the 0th element is at location 2, 2, and is pointing right. That's what this greater than sign means. We're pointing right, okay? And the that is the position of the top of the stack. At row 2, column 2, we have the stack top, okay? Now, if I advance this by stepping through it, so we'll advance by, well, where's the next neighbor? The next neighbor is going to be to the right, so it's going to step over here. And you'll notice when that happened, I'll back up just one step. This is the beginning configuration. And notice what happens to this right here. 2 remains there, but notice that this changes from going right to going down because we've advanced the iterator from going right to going down. And the next neighbor was valid, right? X indicates a valid location. So we move there, 2, 3. It's a valid location which we haven't been to before. And initially we're moving right. Well, if we try to go right from there, there's nothing out here that we can go to. So we're going to try down, left. We can't go left because we've already been there. Up, there's nothing there. So we're done. And once we're done, we pop the stack. And we're going to come back to this location that we were at previously, 2, 2, but now we're pointing down. So we're going to go try to go down, which we can do. And notice that again, 2, 2, the iteration state has changed from down to left. Okay. And so we go down to 3, 2 and pointing right. Well, we can't go right, can't go down. We can go left, so we go left. And I'll keep stepping through this. We're going to go, now let me back up just a second there. Notice we, at this position, at 3, 0, we couldn't go right because we've already been there. We can't go down because it's not a valid location. We can't go left because it's not a valid location. We can go up, so we go up. And notice that now 3, 0 is marked as done. That doesn't mean we've popped it off the stack. It just means if we came back to 3, 0, we would then pop it off the stack because it has no more neighbors to explore. Okay, we'll go right, but we can't go anywhere from here because we've visited all those locations or they're not valid. So it's done. So we pop that off the stack. Okay, we try to go down. We can't go down. Left, no. Up, yes. Okay, then we continue going up, but we're trying right, left, down, up. And then we go right, and then look, we've reached the end location, so we've solved the maze. Okay. Now, just to give you, and this took 31 iterations for us to get from the start to the end. And the path that we found is 2, 2, 3, 2, 3, 1, 3, 0, 2, 0, 1, 0, 0, 0, 0, 1. Okay, that's the path that you should find because if you search right, down, left, up using depth first search, you'll find that path. Now let's look at a different, simpler, but unsolvable maze. I want to show you what would happen if you have an unsolvable maze. Notice there are 6 valid locations here, including the start, which is right here. And there's one ending location. There's 7 valid locations, including the end, but only 6 of them are reachable from the start. So I'm going to kind of race through this pretty quickly and watch what happens. We're backing up. Now look, we're re-exploring spaces that we've seen before. Why are we doing that? Well, because of the nature of this depth first search, we're not saving any of the locations that we've been before. And so we're re-exploring things. That's not the best behavior, but it's the way I want you to implement this project. Okay, and notice that after we explore everything, okay, let me back up one. Once we've explored everything, we get to the end and we pop, the stack is the 0, 0 location, which was our start, is done. We pop it off the stack and there's no solution. Okay, so once the stack becomes empty, there's no solution because we couldn't reach the end. Okay, so a few particulars that I want to point out. For this project, as you've already seen, every location has 4 neighbors, and we're going to move right, down, left, up. And I realized earlier when I was pointing left and right, I may have gotten them backwards, and I apologize for that. We're going to keep track of this, as I've said, with the next direction, which is an integer. Okay, so it's going to, the integer next direction is either going to be right or down or left or up. Look for those constants in the code. There's also a 5th state called done, as we've talked about. And the columns are increasing this way, and the rows are increasing this way, okay? So if we think about right, that's the 0th, down, that's the 1st, left, and up. This is the order in which we would visit the neighbors of this location called loc, okay? Finally, I want to talk about the methods for iteration. There are 4 methods for iteration, like we saw when we talked about iterators in C++. There's an iteration begin method, and this initializes or resets the iteration. It's very simple, but we need it just like we're initializing a variable. And if you think about this, if you want to iterate over all 4 neighbors of a location, you have to call iteration begin first, which sets the iteration state to the initial direction. It sets next direction to the initial direction, which is right. Iteration current tells us what the current location is that is our neighbor. Okay, so it returns the current neighbor. Okay, and of course, it only has a current neighbor if the next direction is right, down, left, or up. It doesn't have a neighbor if the next direction is done. So it should not be called, no one should be calling this function if iteration next direction is done. So that might be a place where you might use an assert to verify that that's the case. Iteration done is a method which simply returns true if the iteration is done. Very simple. And iteration advance is also a simple method which moves to the next neighbor by simply incrementing next direction. Okay. So hopefully, if you've read Project One's description, this will make a lot more sense. Again, download the project's sample implementation that I've provided, use input redirection, use output redirection, and use diff to test your project. And of course, make lots of test cases. Good luck.